Hello everyone. I'm going to present our work on disentanglement and generalization under correlation shifts. So this is joint work with Paul, Jackson, Matthias, Rich, and Matthias. The concept of disentanglement originates from unsupervised learning. Here the goal is to encode the generative factors of the input data in different subspaces of the latent representation. For example, the shape, color, and size of the object are encoded in different latent dimensions. Such disentangled representations are promising in many ways. They can improve fairness and interpretability. Also, they can increase the robustness to out-of-distribution data, and they can help to generate samples in a controlled manner. Most work on disentanglement assumes that the ground truth vectors of variation are independent. This implies that there are no correlations between the attributes. While this holds for simple synthetic benchmark tasks, this is not true for many real-world datasets. For example, the class and the domain can be correlated. This is the case for the street view house number dataset, where lower digits are more common, whereas the distribution is uniform for MNIST. Other examples are the correlation of the foreground and the background of the image, or the co-occurrence of objects. In natural scenes, the occurrence of objects is not random. For example, the computer and the monitor tend to be in the same image. Importantly, correlated data occurs in areas that affect people's lives directly, such as fairness and healthcare. For example, the demographics differ between hospitals. Recent work has shown that such correlations between attributes in the training data can be problematic for learning disentangled representations. Troible and colleague pointed out that for correlated attributes, the resulting latent subspaces encoded a mixture of the correlated attributes. They suggested to address this problem by adding weak supervision. We, however, argued that there is a more fundamental problem that lies in the objective of enforcing independence of the subspaces. In particular, we show that even under full supervision, this objective can fail. Okay, so here's a more detailed description of the problem we want to study. Suppose we want to observe noisy data X that is obtained from a generative process G of S, where S are the underlying factors of variation, which may be correlated with each other. We now wish to find a mapping F to a latent space Z, such that each of the original attributes can be recovered from the corresponding subspace Zk by a linear mapping Rk. Overall, we want that a mapping F is robust to correlation shifts. In particular, we want that a model that was trained on correlated data performs well on uncorrelated or even anti-correlated data. Let's start by looking into a very simple example for which all quantities can be computed analytically. We consider a linear generative model with correlated Gaussian source signals. The generative process is given by the matrix A that describes how the source signals are mixed. Gaussian noise is added in this process. We can now analytically compute the solution for optimal linear regression. We find that the optimal mapping is not equal to the inverse of the generative model, which would be the inverse of A. Instead, it is biased by the correlation structure CS and by the noise structure Cn towards direction of maximal signal-to-noise ratio. This sensitivity to noise becomes a problem when considering predictive performance under correlation shift. We find that the variance explained drops when the correlations change during testing. The reason for this is that the estimator makes use of the correlation that is present in the training data to counteract the information that is lost due to the noise. However, this correlation is no longer present in the uncorrelated test data, which results in wrong predictions. The problem of pure linear regression is that there's no constraint that prevents the model from encoding both S1 and S2 into each of Z1 and Z2. A common approach to fix that is to enforce independence by minimizing the mutual information between latent subspaces. However, there's a problem. There are correlations between the source signals S1 and S2. By making the latent subspaces independent, at least one of them cannot contain all relevant information about its attribute anymore, and therefore will have poor predictive performance. The effect of this issue can be seen very clearly in the results shown in the table. Enforcing unconditional independence does not even lead to good performance on correlated in-distribution data. So we have seen that enforcing unconditional independence between the latent subspaces does not solve the disentanglement problem. So how can we fix this? To improve robustness to correlation shifts, we wish that Z1 and Z2 share as little information as possible. More specifically, we want that the latent subspaces share only the information that is necessary to account for the correlation that is present in the training data. To understand this better, let's take a look at the graphical model. We assume that there must be a common cause for the correlation between S1 and S2. This common cause provides a connection between Z1 and Z2 that introduces the statistical dependence. We can see that observing either of the source attributes disconnects the latent subspaces. We can make use of this by adapting the objective, such that we minimize the mutual information between the latent subspaces conditioned on the attributes S1 and S2. This states that if we know S2, then knowing Z1 does not give us more information about Z2 and vice versa. When we now look at the performance under correlation shift, we see that conditional independence leads to robustness under correlation shift. Next, we investigated the impact of the correlation strength and noise level on the optimal solutions obtained by the 3 different objectives that we just discussed. As before, we used the synthetic regression task. First, let's look at the results for the base objective, which corresponds to optimal linear regression. In each subplot, we show the variance explained, where higher is better, independence of the noise level. The magenta line shows the results on the correlated training data, whereas the green color corresponds to the correlation shifted test data. The dark green curve shows the performance on uncorrelated test data, while the shaded green region shows the spread of performance over test data with varying correlations from anti-correlated to correlated. The strength of the correlation that was present during training increases, moving from the top row to the bottom row. In general, for all training correlation strengths, as the noise level increases, performance decreases as it's harder to predict desired attributes. In the bottom row, for strong correlations and intermediate noise levels, we find that there is a large gap in the performance between training and test data. The reason is that the model exploits the correlation structure that's present during training and thus fails when evaluated under correlation shift. For base plus MI, where we minimize the unconditional mutual information, in addition to the regression loss, we find that it performs well when no correlation is present during training. But as we increase the correlation strength, the model fails in the in-distribution data for a wide range of noise levels. This is because by satisfying the unconditional MI constraint, the model cannot capture the relevant information about each attribute in the corresponding subspace. Minimizing the conditional mutual information, in contrast, yields an optimal solution which is robust to correlation shift. It maintains consistent performance across all training correlation strengths and noise levels and matches the reference curve from the uncorrelated setting. In some cases, like linear regression with Gaussian variables, we can compute the mutual information and the conditional mutual information analytically. However, in most cases, there are no closed form solutions. So on this slide, we are going to describe the approach that we use to minimize conditional mutual information in general classification settings. The CMI between 2 random variables x and y given z is 0 if the joint distribution conditioned on z is equal to the product of marginal distributions conditioned on z. So the idea is to align the distributions adversarially. Our approach works as follows. Say you want to minimize the conditional mutual information given an attribute, for example, a sub 2. First, we sample a mini batch of examples that have a particular value for A2 and pass them through the encoder to get a mini batch of latents. We can now minimize a supervised objective using separate classifiers on the corresponding latent subspaces. Also, this mini batch of latents gives us samples from the joint distribution conditioned on A2. To obtain samples then from the product of marginal distributions, we batch shuffle the latent subspaces. The idea here is to shuffle subspaces such that we combine the subspace Z2 from one example with the subspaces Z1, Z3, Z4 from another example. We can then train a conditional discriminator to distinguish between these shuffled and unshuffled latent spaces. Then we are training the encoder adversarially to make these 2 distributions hard to distinguish. We applied this adversarial approach to minimize CMI for a real-world example based on CelebA. Here we consider 2 attributes from CelebA that we know are causally related. Those are male or female and smiling or not smiling. We consider 2 ground truth vectors of variation that generate phase images, and we wish to learn a latent space partitioned into 2 subspaces from which we can linearly decode these attributes, male, female, or smiling, not smiling. We generated correlated training data by subsampling CelebA. In this example, the training data is correlated such that the majority of men are smiling and the majority of women are not. The pattern is reversed in the test data, which allows us to test on anti-correlated test data. We don't add any observation noise here because this real-world example is already noisy. Now we evaluate our 3 objectives on a range of training correlation strengths. In the left subplot, we compare the performance on data that has the same correlation structure as the training data. In the other two subplots, we evaluate the models on an uncorrelated and on an anti-correlated test dataset. We find that the base objective performs well on the correlated validation data, but the performance drops under correlation shift. As expected, base plus MI fails to model the in-distribution validation data. And in contrast, conditional mutual information minimization achieves the most consistent performance across correlation strengths for both of the correlated shifted test sets. And finally, I would like to show that one can see the negative effects from correlations already on the correlated in-distribution data. So here we evaluate the performance on subpopulations. The idea is that there are some combinations of attributes that are more common than others, and models that exploit these for prediction may treat rare combinations unfairly. And that's exactly what we observe for the base objective. It performs well on the common combinations, but fails on rare attribute combinations. Base plus MI doesn't even succeed on the common combinations, and base plus CMI performs well on the common combinations. But importantly, it also lowers the error rate on the rare combinations relative to the base model. So in summary, learning robust disentangled representations can be challenging in the presence of correlations, even when we have full supervision. We introduced a motivated subspace independence conditioned on the attributes as the correct objective for disentanglement in correlated settings. We described an algorithm to achieve conditional independence for general classification tasks. And all in all, we showed that CMI minimization improves robustness to correlation shifts on both synthetic tasks and real-world datasets. Thank you.
Any questions? Yeah, any questions from the people in person? If not, just because we're a bit late anyway, we might just stop for the lunch break. But for each paper, there is a Slack channel, or you can just reach out to the authors directly on Slack, and you can pick up the conversation.